So the first thing I want to go over before we hit the quiz is let's look at like stud spacing or joist spacing. Let's say we have a 4-foot wall and we want to space our studs 1 foot apart. How would we figure out how many studs it would take to do that 4-foot wall? What would you do? Four divided by 1, right? 4 feet, 1 foot apiece. 4 divided by 1 is 4. But will it really take 4 studs for that wall? No. What's going to be different? So if this is a 4-foot wall, you have a stud at 1 foot, another one at 2 foot, another one at 3 foot, and another one at 4 foot. Well, there's our 4. What's missing? 1 at the beginning. When you just divide, you miss the 1 at the beginning. So when you divide that out, you have to add 1 to it. Just like if we had roof trusses. Let's say 2-foot spacing. OC stands for on center. So if they're 2 foot on center and we have a 40-foot roof, that's not the span, that's the run. So we're looking at like this, 40 feet here. Trusses are going that way. How do we figure out how many trusses we need? 40 divided by 2 gives us 20. And then, of course, we still have to add 1. It's going to be 21 trusses. This adding 1 is when we need 1 at both ends. We needed 1 at the beginning and at the end. There are other cases, though, if we're looking at beams. So let's say we have a 30-foot span basement, and we're going to have a beam every 10 feet going this way. 30 divided by 10 gives us 3, but do we need 3 beams? Well, we need 1 here, 2 here. Do we need 1 down here? No, there'll be a wall there. We don't need 1 up here. So when we don't need 1 at either end, we actually subtract 1. We only need 2 beams. And again, that's because we don't need 1 at either end. We subtract 1. The same is true for posts. Let's again look at a 40-foot run here. We want a post every 8 feet. How do we figure out how many posts we need? 40 divided by 8 is 5. So if we're looking at our beam across here, we have 1 at 8 feet, 1 at 16 feet, 24 feet, 32 feet. Do we need 1 at 40 feet? No, we've got a wall there. We don't need 1 here. So we subtract 1 again. We only need 4 posts. So it's a concept I wanted to make sure we went over before you hit this quiz, that quiz 2 that I gave you last Friday. So have you guys work on that for a while, and then we'll move on to new material in probably about 10, 15 minutes. Okay, so our new topic for today is we're going to move on to decimals. We've pretty much finished up fractions. So we want to look at that next form of numbers. And the key to decimals, just like with whole numbers, was place value. So just a review of our place values for whole numbers. This last place value here before the end of the number is called the ones, then tens and hundreds, then 1,000s, tens, 10,000s, and the hundreds or 100,000s. We'll stop there. Now I wrote them out numerically this time so that you can see the pattern. Every time I move a place value to the right, the value of that place is divided by 10. 100,000 divided by 10 is 10,000. 10,000 divided by 10 is 1,000. And it keeps going. 100 divided by 10 is 10. 10 divided by 10 is 1. As we go to the other side of the decimal point, or continuing on after what many would consider to be the end of the number, that pattern continues. 1 divided by 10 is 1/10. 1/10 divided by 10 is 1/100th. And 1/100th divided by 10 is 1,000th. Then 1/10,000th and 100,000th. Now, as we're looking at those place values, they look a lot like fractions because that's exactly what they are. They are just a short way of writing common fractions that have denominators that are powers of 10. So if I have a fraction like 0.68, that is, or a decimal, I should say, of 0.68, that literally is a fraction where the numerator is the number that's after the decimal point, 68, and the denominator is the place value of that last digit, hundreds. So that fraction would be 68 hundredths. Now, of course, as a fraction, we would reduce that. Both of those numbers can divide by 4. 68 divided by 4 is 17. 100 divided by 4 is 25. So 0.68 is equivalent to 17/25. But we can write it as a decimal if we can convert it into that fraction with a common, those denominators of powers of 10. We'll look more at that if converting decimals into fractions later. For now, we want to jump into operations with decimals. So if I have something like 4.83 plus 27.6, if I go to set that up, what do I have to be careful to make sure I do? Line up the decimal point. Remember we said when we add or subtract, we must have the same name. So I wrote the top number first, then I put in the decimal point for the bottom number and filled in the number around it. That helps me make sure I have everything lined up. Now I really should fill in this 0 here after the decimal point to make sure they both have the name of hundredths and have a hundredths digit. So when I go to add here, I have 3 plus 0 is 3. 8 plus 6, 14. So I'm going to keep the 4 and carry the 1. Now before I can do the 1, 4, and 7, what should I do? Bring the decimal down. Remember, when we add or subtract, we keep the same name. Bringing the decimal straight down was just keeping the same name. 1, 4, and 7, 12. So we keep the 2 and carry the 1. And of course, 1 and 2 is 3. 32.43. Not going to do any more examples of addition because I'm pretty sure you guys have seen enough of that in your life. And decimals are the one form of numbers that go into the calculator really easy. So even the cheapest, most basic calculator can do decimals pretty well. So for subtraction, we have the same thing. We might have 34.2 minus 9.67. When we go to set that up, 34.2, we have to make sure we line the decimal points up again. So I put the decimal point in for the bottom number, and then I fill in the digits around it. Here we have to put in the 0 that's missing for that decimal place. And then we'll go to subtract. 0 minus 7 can't be done, so we need to borrow from the 2. That's a 1. This is now 10. 10 minus 7, 3. 1 minus 6, have to borrow. This will be 3. This will be 11. 11 minus 6, 5. And then bring the decimal down. So we still bring the decimal straight down to keep the same name. Notice the decimal point did not affect our borrowing or the carrying over here at all. 3 minus 9 can't be done, so we borrow. This is 2 and 13. 13 minus 9, 4 and the 2. So 24.53. One last subtraction example I want to do is something that looks like this. 8 minus 2.4382. So when we go to write this out, where is the decimal point for the 8? It's at the end. Anytime there's not a decimal point on the number, that means it's at the end of the number. So we line up the decimal point for the 2.4382. And again, we have to fill in those missing decimal places, putting in zeros. We go to subtract here. 0 minus 2 can't be done, so we need to borrow. But there's nothing here to borrow, so we have to do what? All the way to the 8. So this will be a 7. That would make this a 10. We need to get it all the way down here, so we have to keep borrowing. So that's 9. This is now a 10. Borrow again. 9 and 10. One more time. 9 and 10. Now we can go ahead and subtract. 10 minus 2, 8. 9 minus 8, 9 minus 3, 6. 9 minus 4, decimal, and 7 minus 2 is 5. Perfect. When we multiply and divide, do we need the same name? Careful. No. We don't need a common denominator with fractions. We don't need the same name with our decimals. Don't have to line up the decimal points. So I can have 3.24 times 5.9 and not worry about lining up the decimal points. So we'll do 9 times 4 is 36. There we go. So 6, carry the 3. 9 times 2, 18 plus 3, 21. So 1, carry the 2. 9 times 3, 27 plus 2, 29. So 9, we carry the 2. There's no place to go, so we just put it there. Now we're done with the 9. We move over to the 5. What do we have to make sure we do down here? Put in a 0. And then I usually put a line up here, again, to make sure I remember that those are old carries. Any new carries will go above the line. So now, 9 times 4 is, oops, not 9 times 4, 5 times 4. 20, so 0, carry the 2. 5 times 2, 10. Now the 2 is above the line, so plus 2 is 12, so 2 carry the 1. 5 times 3, 15, plus 1 is 16. And then we go ahead and add those together. We got 6, 1, 11, so 1 carry the 1, 9, and 1. Where's my decimal point go? Between the 9 and the 1, right? How do we figure that out? Yeah, we have 1, 2, 3 digits after the decimal point. So in our answer, we count from the end, 1, 2, 3 digits after the decimal point. Remember, the reason we're doing that is because we're combining the names. This is hundredths. This is tenths. Hundredths times tenths makes thousands. Now remember, we did talk about that estimating. This is about 3. This is about 6, right? What's 3 times 6? 18. So that is the only place that makes sense for that decimal point to go. 1.9116 would not make sense. It's way too small. And 191.16 is way too large. So you can use that estimate to make sure you've got your decimal point in the right place as well. I will warn you about this. Most calculators, the decimal point is one of the first keys to start malfunctioning. So be very careful. And on many of the older calculators, the decimal point doesn't show up till you hit the next key. So it's hard to tell whether it registered or not. So be very careful with the decimal points. Let's look at division. Let's try 72.348 divided by, let's go 3.2. And let's go to the nearest thousandth. How do I divide by a decimal? The answer is we don't. How do we make it so we don't have to? We can actually divide by a decimal, but remember that process I showed you on the first day of that whole long, what's the place value and all that stuff? That's exactly how you divide by decimals. Well, in order to avoid that full process, we came up with a shortcut where we avoid dividing by decimals by getting rid of it. So how do we get rid of that decimal? Yeah, we move it over. Then what do we have to do? Yeah, if we take whatever we're dividing by, in this case the 3.2, and we move the decimal to the end. However many places we had to move it there, we have to move it over here as well. So this is now 723.48 divided by 32. Why are we able to do that? Well, we've mentioned that fractions and division are kind of interchangeable. So if we turn that division into fractional form, if I wanted to move the decimal point down on bottom, I just have to multiply by 10 to make it 32. Multiplying by 10 moves the decimal point one spot. But if I multiply the bottom of the fraction, I have to multiply the top. 72.348 times 10 is 723.48. So when I turn that back into a division problem, that's what ends up. So moving those decimal points the same amount in each, all that is going through this whole process of making it a fraction, changing its name, and then converting it back. So now then, does 32 go into 7? No, so we'll leave it blank above the 7. Does 32 go into 72? Yeah, twice. Now 2 is the last digit we use, so we put the 2 above the 2. What's 2 times 32? 64. We subtract there to get 8. Then what? Bring down the 3. Does 32 go into 83? Twice. 2 times 32 is still 64. We subtract, we have 19. Now what? We're going to bring down the 4, but before we bring down the 4, we have to make sure we move the decimal point up. When we're dividing, just like addition and subtraction, we can't cross the decimal point without moving it into our answer. Now we'll bring down the 4. 32 into 194. Let's try 6. What's 6 times 2? 12, so 2 carry the 1. 6 times 3? 18 plus 1 is 19. That does work. And there's 2 left over. Now we'll bring down the next digit, the 8. Does 32 go into 28? No. Now we use the 8, so we have to have something above it, so we put in a 0. We're out of digits. Does that mean we're done? No. If we're after the decimal point, we can add as many zeros as we want to, and it doesn't change the value of the number. 723.48 is the same value as 723.48000000. The exception will come in a few weeks when we talk about measurement. Then we've got to be careful with those. But for now, we can add a 0 and bring it down. Does 32 go into 280? A couple of times. Let's see. I think 9 would be too big. Let's try 8. So 8 times 2 is 16. 6, carry the 1. 8 times 3, 24 plus 1 is 25. So yes, we have 24 left over. Now we said we wanted it to the nearest thousandth, so that's the thousandths place. Can we stop there? No. What do we have to do? Add another 0, bring it down. 32 into 240. Let's try 7. 7 times 2 is 14, so 4, carry the 1. 7 times 3, 21 plus 1 is 22. That's 16 left over. So 7 was correct. We had to go this next digit because when we say we want it to the nearest thousandth, it's saying round it to the nearest thousandth. And we can't round without knowing the next digit. So now, to the nearest thousandth, this is the thousandth digit. The 7 tells us that this is going to become 609. The 7 says we round that up to a 9. So 2.609. Perfect. Any questions there? Okay. Now, there are some things with decimals that are very similar to whole numbers. If I had 2,000 times 40, I can take the 2 times 4 to get 8. How many zeros do I have to put after it? 4. We got the 4 zeros because there's 1, 2, 3 zeros here and 1 0 there. We add them together. 3 plus 1 is 4. So we put 4 zeros in the answer, right? So if we have 30,000 times 2,000, that's going to become 6 with how many zeros? 7 zeros. Again, 4 zeros plus 3 zeros makes 7 zeros in our answer. When we multiply 0.002 times 0.04, what's 2 times 4? 8. Instead of zeros, we're counting decimal places. We have 1, 2, 3. Here we have 1, 2. So our answer has to have 1, 2, 3, 4, 5 decimal places. So 0.00008. Or like this one, 0.00003 times 0.0002. 3 times 2 is 6. How many decimal places? Careful. 7. So that's 1, 2, 3, 4, 5, 6, 7. So 0.000006. Instead of adding the number of zeros to get the zeros in the answer, we're adding the number of decimal places to get the decimal places in the answer. That's just the equivalent of being after the decimal point. And it's actually the same rule, because here, this is a name of 10,000s times a name of 1,000s. 10,000s times 1,000s is 10 millions. Well, this is the name of 100,000s times 10,000s. 100,000s times 10,000s is 1 billionth. This is tenths, hundredths, thousandths, 10,000ths, 100,000ths, 1 millionths, 10 million. Something went wrong there. I have an extra zero in there, don't I? Yes, I do. No, I don't. What did I get wrong? Oh, I counted my decimal places wrong. That's why. You were correct when you said 9. This should have been 5, and this should have been 4. So yes, that should have been 9, so it would have been billions. Tenths, hundredths, thousandths, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions. It's a Friday afternoon. The little hamster stepped off the wheel a long time ago. For division, we have something similar. If I have 800,000 divided by 200, we do 8 divided by 2 is 4. Now this has 5 zeros and this has 2 zeros. How many zeros are in our answer? We're dividing. So it's the reverse. Instead of adding the zeros, we subtract. 5 minus 2 is 3. So it'll be 4,000. Or if we have 60,000 divided by 3,000. 6 divided by 3 is 2. How many zeros in that answer? 1. This had 4, 3. 4 minus 3 is 1. Same is going to be true then of our decimal places. This has 5 decimal places. This has 3 decimal places. 8 divided by 2 is still 4. Now we subtract the number of decimal places. 5 minus 3 is 2, so that'll be just 0.04. Or 0.0006 divided by 0.003. 6 divided by 3 is 2. This is 4 decimal places minus 3 decimal places. This has to be just 1 decimal place. It's just 0.2. So the decimal places play the same role as the zeros do in the whole numbers. Powers. We know that 2 squared is what? 4. Be careful with this one now. 0.2 squared, that's what most people will say, but 0.04. Because this is 0.2 times 0.2. 1 decimal place, 2 decimal places. We've got to have 2 decimal places. Or 0.12 squared. We know that 12 squared is 144. Good. How many decimal places does this have to have? Starts out with 2. We squared it, has to have 4. So that's 0.0144. If I go to a higher power than that, to the power of 3, well, that's 0.2 times 0.2 times 0.2. Well, 2 times 2 times 2 is 8. How many decimal places does this have to have? You got it. 1, 2, 3. So 0.008. If it were 0.02 to the power of 3, well, 2 to the third power is still 8. How many decimal places does this have to have? Careful. 6. So 1, 2, 3, 4, 5, 6. It needs 5 zeros between the decimal point and the 8, but it has to have 6 total decimal places. We'll have you work for a few minutes here before we take our break. In the little book, units 11, 12, 13, and 14, the odds. Again, the first few problems are just simple, calculator problems, basically. If you want to skip those, make sure you do the word problems. That'll be fine. We'll take a break in about 5 minutes. We'll work on this for just a little bit. So I want to talk about converting next. We'll start off with converting a fraction to a decimal. We've mentioned that a fraction and a division problem are interchangeable. So 3/4 can be thought of as 3 divided by 4. And of course that gives us what is a decimal? 0.75. Most of us knew that one. We didn't have to calculate it out. But if we did need to calculate it out, we could do the long division like this. 3 divided by 4. Well, 4 does not go into 3, so we leave it blank above the 3, and there's nothing left. But remember, we said we can add zeros, but we can only add zeros if it's after the decimal point. So we have to put the decimal point in and bring it up. Now we can add a 0. 4 goes into 30 how many times? 7. 7 times 4 is 28. We subtract to get 2. Then we can add another 0. We bring it down. 4 goes into 25 times. So there's our 0.75. We might have something, let's make it more interesting. Let's do 7/16. If I need to turn that into a decimal, it's 7 divided by 16. Does 16 go into 7? No, so we leave it blank above the 7. And we're at the end of the number, so we put in the decimal point and add a 0. Does 16 go into 70? 4 times 6 is 24. Carry the 2. 4 times 1 is 4. Plus 2 is 6. So 64. So we subtract and we have 6 left over. And we'll add our 0 and bring it down. 16 goes into 60. 3 times. 3 times 16 is 48. We subtract to get 12. Add another 0 and bring it down. 16 goes into 120. Well, we'll just try some. 5 times. Let's try 5 times 16. 5 times 6 is 30, so 0 carry the 3. 5 times 1. 5 plus 3 is 8. Too small. 7. So 7 times 6 is 42, so 2 carry the 4. 7 times 1 is 7 plus 4, 11. That looks like a winner. So 7, and this would be 112. We would subtract to get 8. At this point, we're starting to wonder, do we need to worry about rounding it, or do we keep going? Well, we'll go one more here. Add a 0 and bring it down. 16 goes into 80. Exactly 5 times. So that's the end of it, right? There you go. So 0.4375 is equivalent to 7/16. Now, when we're doing this conversion, what we want to watch, or this division, what we want to watch is what's left over here. That was different every time. And as long as that number keeps being different, we know that there's a chance that this will terminate or end. Very few decimals keep going on forever without having some sort of pattern. If I have 5/7, and I go to divide that, 7, oops, wrong way, 5 divided by 7. Of course, 7 does not go into 5, so we add the decimal point and a 0. 7 into 50. 7 times. 7 times 7, 49. 1 left over. Add a 0 and bring it down. 7 into 10. Once. 1 times 7. 7. What's left? 3. Add a 0 and bring it down. 7 goes into 34 times. 4 times 7. 28. 2, right? Another 0. Have we seen a repeat? We started with 5, we had 1, we have 3, we have 2. They're different every time, isn't it? So we should keep going. 7 goes into 20 twice. 2 times 7, 14. What's left? 6. Is that still different? It is. So add another 0 and bring it down. 7 goes into 60. 8 times, does that look right? 8 times 7 is 56. What's left? 4. Is that different? Yeah, right. 5, 1, 3, 2, 6, 4. Still different. So add a 0 and bring it down. 7 goes into 40. 5 times, right? 5 times 7 is 35. What's left? 5. Now, that 5 is what we started with. So that tells us we're probably going to see a repeat here. Let's just go a little bit further to make sure that's what happens. If I add a 0 and bring it down, 7 goes into 50. 7 times, that's 49. And 1 is left over. Now we look up. We had 5 here, and 1 was left over. We had 5, and 1 was left over. It's going to repeat. So what that tells us is this will be 0.714285. And how do I indicate that they repeat? Put a line across all of them. From 7 to 5. All 6 of those digits will repeat. 0.714285, 714285, over and over again. We might have something like this. 5/12. So 5 divided by 12. 12 doesn't go into 5, so we leave that blank and add the decimal point and add a 0. 12 into 50. 4. 4 times 12. 48. There's 2 left over. And then 0, bring it down. 12 goes into 20. Once. 1 times 12. 12. What's left? 8, right? And then 0, bring it down. 12 goes into 80. 7 times, not, yeah, 7, no, 6, sorry. 6 times 12 is 72. What's left? 8. There's our red flag. 8 twice in a row. Double check it. 0, bring it down. All 12 still goes into 80. 6 times. 6 times 12 is still 70. 2. We're going to have 8. So this 6 is going to keep repeating. So how would we indicate that one? Only over the 6. Perfect. 0.416, just the 6 repeating. How about 9 over 110? So 110 doesn't go into 9, so we add the decimal point, add a 0. Does 110 go into 90? No, so we got to put a 0 up. Add another 0 here. How about 900? 8 times. It'd be 880. This would be 8, 9, 10. That would be, I don't need the 10, I guess. 8 and 10, that would just be 20 left over, right? Add a 0 and bring it down. 110 goes into 200 once. 1 times 110 is 110. What's left? 90. Bring the 0 down. Add a 0, bring it down. Well, there again, this is 90. Now, this was a 9 we started with, but we did add a 0 to it. Let's see if we get the same thing. That would be 8, which 8 times 110 is 880, and there's 20 left. That is what we had here. So this would be 0.081, where the 8 and 1 repeat. Look familiar? Okay. Now we need to go the other way, from a decimal to a fraction. We kind of saw a hint of this earlier, where if I have 0.0375, the numerator of my fraction is the numbers that are after the decimal point. So just 375. What's my denominator going to be here? 10th, 100th, 1000th, and yes, 10,000. So 10,000. One way to double check here is there's 1, 2, 3, 4 decimal places. 1, 2, 3, 4 zeros in my denominator. Both of those can be divided by what? So somebody said 5. 25 would work too. 5 would give us 75 here and 2,000 here. They can both still be divided by 25, okay? 75 divided by 25 is 3. 2,000 divided by 25 is 80. 3/80. What if I have 4.5625? The 4 that's out front, we're just going to ignore. That's a whole number. Just like a mixed number with our fractions, this is a mixed number with our decimals. This is going to be 4 as the whole number, and the part after the decimal point will become the fraction. So we have the 5,625 over 10,000 again. Both of those can be divided by 25 will work again. So let's see here. 5,625 divided by 25 is 225. 10,000 divided by 25 is 400. So the trick there for the 25 is just 100 is divisible by 25. That's 4, and you're still left with the 2 zeros. Up here, it's a little trickier. You just have to go through and carry quickly. But both of those are still divisible by 25 again. 225 divided by 25, 9. 400 divided by 25, 16. So this is 4 and 9/16. So we have to remember the whole number part. Not so bad. So this process up here is if we're asked to convert to an exact fraction. And we just use the place value of that last digit to become our denominator. But in practical applications, especially in wood construction, 3/80 is not on this tape measure anywhere. 9/16 is, but many times, if we try to convert to an exact fraction, we're going to get a number that's really not useful to us. For example, if I have 0.713 inches, now let's do this, 712 inches, and I want to convert that into an exact fraction, well, that's be 712 over 1,000. Both of those can divide by, let's try 2. 712 divided by 2 is 356. 1,000 divided by 2, 500. Both of those can still be divided by 2 would work again. 356 divided by 2 is 178. 500 divided by 2, 250. Can we divide by anything else? They're both still even. Divide by 2. 178 divided by 2, 89. 250 divided by 2 is 125. That's where we stop. Well, 89 1/25 doesn't do us a lot of good in construction. Where's that on the tape measure? I have no clue. So when we're dealing with construction, a lot of times we don't want an exact fraction. We want to go to the nearest given denominator. In this case, let's go to the nearest 16th of an inch. Well, if that's the case, what we're going to do is a totally different process than what we did here. We're going to start with the 0.712, and we're going to leave the decimal point in it. And we're going to make it into a fraction the simplest way that we can make a fraction. That's by putting it over 1. Now, it's a fraction with a denominator of 1, but we want it to have a denominator of 16. How do we make that happen? Multiply by 16. 1 times 16 is 16. Have to do the top as well. 0.712 times 16. Come on. There it goes. Is 11.392. What that 11.392 tells us is that this is between 11/16 and 12/16. Which is it closer to? Yeah, it's 11.3, so it's the 11/16. So 11/16 of an inch is close enough to what we want there. So that's what we're going to use it as. We went over this a little bit with the stairways last Monday. So it's very important to keep these two processes straight. If I'm asking you to go to an exact fraction, or if I want you to go to a nearest given denominator. Now, if we were doing stairways, and this is what it came out to, is 11.39, we would want to be very careful how we measured that out and how we did that, because it is kind of close to the middle. 11.39, the 0.39 is about 1/3 of the way to the next one. So if I were cutting stairs, and let's say that dimension was 7 11/16 is what that came out to be, 7.712. What I would do when I was cutting stairs to correct for that is I would cut this one 7 11/16. This one would be 7 11/16. But because that's 1/3 of the way to the next higher number, to correct so that we didn't get too small as we went through, because what's going to happen here is if I go 7 11/16 again, after 3 rises, I have lost a full 16th of an inch, which isn't a big deal there, but what if this has 12 rises? Well, every 3 is going to be a 16th of an inch. That's going to be 4/16 or a 1/4 inch of a difference. You don't want your bottom step to be a 1/4 inch lower. 1/4 inch does not sound like much, But if you've ever gone down a stairway that's off by that much, you hit that bottom step and it's a quarter inch shorter. You ever have that? You hit the bottom and it's like a jar up through your legs. It's really different to have that step shorter. So what I would do is, since we're about a third of the way to the next one, is that would be 12/16 or 3/4. Then 7 and 11, 7 and 11. The next one again, 7 and 12. I'd add a 16th to every third one just to correct for that. Being off a 16th of an inch every few steps is way better than being off a quarter or more at the very bottom or at the very top, either one. Okay, so I hate to give you guys 2 quizzes in a day, but unfortunately that's where we're stuck at here. So I'm going to give you a quiz, and then when you're done with the quiz, your homework, you do still have the homework out of the little book, those units 11, 12, 13, 14. And then, oops, there's actually one more thing I got to go over here. Sorry about that. I almost forgot. This isn't the machine tool. This is the construction group. So for construction, a big application of decimals is the transit. How many of you guys have ever worked a transit? How many know what a transit is? A couple of you? Okay. A transit is kind of like a rifle scope. You sight through it, only it's on a base that you can level. It has screws where you can level. So you want to turn it and you want to get it level. So as you spin it around, it's level, and no matter what direction it points in. There are tricks to getting them level. If we had one, in fact, I might try to bring mine in sometime and we'll take a look at it and we'll show you how to level it and how to use it. Anyway, you get it perfectly level. Then you sight through it. It almost looks like a person, doesn't it? My art's getting better. Don't count on that being a consistent thing. So, somewhere out here then, you have a surveyor's rod or a surveyor's stake. It's basically, it could be as simple as a tape measure that has been pulled out, cut off, and attached to a stick or whatever. A tape measure is a little hard to read if you're going to get very far away from the scope of the transit, just because the writing is a little small on it. But you could read it. Typically, the surveyor's rod is not done, like a tape measure is in quarters, eighths, sixteenths, and so the surveyor's rod is usually done to 1/10 of an inch or to 100th of a foot, depending on what your application is. So let's say this one is reading that distance, let's call it 53.6 inches. If I put another rod here, I'll put this one in blue. Would I expect the reading on this rod to be larger or smaller than 53.6? The distance from the ground to my line of sight, is it bigger or smaller? It's bigger. I would expect this number to be bigger. This might be like 59.2 inches. The bigger number, larger number here, means a lower elevation because it's further down from the line of sight to the ground there. That's one of the biggest mistakes people make when reading a transit is they get that backwards. They think, oh, it's lower, I'm going to subtract. 6 inches lower, I'm going to subtract 6 inches. That's not true. 6 inches lower, you have to add 6 inches because you have to go down that much further. The transit is not necessarily measuring absolute height. It's measuring how far it is down to that point. So, of course, here, if I subtract those two numbers, what's the difference in elevation there? 5.6? You want to borrow 5.6 inches in difference. So if I'm reading my transit, and I have a reference point here that is 49.7 inches. And I need to fill this in here so that it is 8.5 inches lower than this point. when I run my reading here, what's this going to have to read? Careful. To get lower, we have to add. The number gets larger because it's further down. It's 2 carry the 1. That'll be 58.2. So be very careful with those. Reading the surveyor's rod. Typically, like I said, it's either marked in 1/10 of an inch or 100th of a foot. Either way, it's hard to make it so it's visible. If they just did this, let's say this is 27 inches, and they did 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that's 28 inches. Those little lines are tough to see through that scope if you get very far away. The scope does have a little bit of magnification, but not a lot. This would be the easiest way to read it, but if I make those lines fatter so it's easier to see, let's say I do this with my lines. So it's easier to read. Can anybody see the problem here? Even if I get to manage to space them the same, I didn't get them perfect, but it's close enough. So over here, if there's my scope, my line is sitting like this, that's reading 27.5, right? Because it's right on the line. But here, if I want it to be 27.5, is it here? Is it up here? Is it trying to be right in the middle? Well, trying to get something right in the middle is tough to do, isn't it? It's easier to put it on an edge. So what they do in most cases, most surveyors' rods are set up like this. Let's say this is 42 inches. There'll be a line like that, colored in. And what they'll do is 42 inches is actually to the top of that line. Pretend my coloring is not terrible. And these marks that they put on here, of course that's not going to be enough room, is it? The marks they put on here, the width of the mark is exactly the same as the spacing between the marks. So this is going to be 43 here then. So like I was saying, the width here is exactly the same as the spacing between. Same as that space, same as that width. So if this is 42 inches, the bottom of this line is 42.1 inches. The top of the line is 42.2. The bottom of this line is 42.3. The top of the line is 42.4. Bottom of this line is 42.5. Top is 42.6. Bottom of this line is 42.7. Top is 42.8. Bottom of this line is 42.9. And just like the top of the other one was 43, the top of this one is 42. The top of this one is 43. So each line is actually 2 measurements. The bottom of the line is 1 and the top of the line is 1/10 higher. Make sense? So that way it's way more precise if you're lining up your scope with the edge of a line instead of trying to figure out where the middle is. If this were measured in feet instead of inches, it's going to work pretty much the same way. This might be 3.8 feet. Well, they're the same thing. This is 3.81, 3.82, 3.83, 3.84, 3.85, 3.86, 3.87, 3.88, 3.9, and 3.89 and 3.9. Does that kind of work out? Okay. Those will appear in your homework, so that's why I wanted to make sure I get those put on there. So anyway, back up here, homework, little book. Unit 15. Then I'll give you the quiz to work on, and then we'll have homework time for the rest of the period.